All right. Thank you so very, very much. This is the ins and outs of SQL Server data compression. And I just said thank you, but I'm actually going to put up a thank you slide here now if PowerPoint cooperates. There we go. Just want to say thank you to the organizers who make this event happen and for having me and all you attendees out there who are watching this because it's kind of hard to have a conference without people watching it. Also want to give a shout out to Mr. John Morehouse, who will be acting as my moderator today. So feel free to ask questions at any point. John will either try to answer them himself or he will butt in at the end of each section and we can have a little chat about that and then we'll do even more at the end. So thank you so much. And finally, a little advertising note here. I would like to point out that there is official 8KB merchandise, these lovely Mixed Extents t-shirts promoting the Mixed Extents podcast, which is brought to you by the creators of 8KB. So if you want to be cool, well, if you want to be cool, first of all, don't do anything at all that I do. But if you'd like to be cool and help this event, check out their little store they got there, and they got these awesome shirts. And maybe someday they'll have like 8KB laptop stickers or something like that. Hint, hint, hint. All right, to briefly introduce myself, my name is Bob Pusateri, coming to you here from Chicago. As we like to say, Chicago, come for the deep dish pizza and the Italian beef sandwiches and stay because you died of coronary artery disease. I've been active in the community for a while. I've run user groups. I help plan events in the Chicago area. I've been working with SQL Server since the Microsoft Certified Master Program was a thing, which is just a nice way to say I'm not a spring chicken anymore. And the next time I go job hunting, potential employers are probably going to be trying to see if they can find someone a little younger first. But seriously, the best thing on this slide is my contact information. So if you have any questions we can't get to at the end of this session, or if you're watching a video of this and would like to reach out later, find me on Twitter. It's got my email address on there, or you can go to my blog, bobpusateri.com, and I got a contact me page, which will also send me an email. So our agenda today, this morning, this afternoon, evening, night, depending on where you are, we're going to go through just some very basics of compression in general, just talking a little bit about the technology, and then we'll actually get into SQL Server specific topics. We'll talk about row and page compression, how those work, and then we'll talk about Columnstore and how that works as well. And then we have time for questions at the end, hopefully. All right, so why are we compressing? Disk space is pretty cheap, right? I mean, you can go to your local tech store and get 12 terabyte drives or even larger at this point for not a whole lot of money. But unfortunately, enterprise disk space, the disk you can really depend on, well, that's not cheap, right? Because you're paying for not only usually really good quality hardware, but you're also paying for support. And when you have a problem, there's someone there to pick up the phone and help you now. So disk space, it's gotten cheaper, but the disk space that you're depending on, not as much. And that's for very good reasons. So compression originally came out as a way to enable you to store more data in less space, and that's what was built in with SQL Server, right? Additionally, compression can help in terms of maintenance, right? You have maintenance processes like DBCC, CheckDB, and whatnot. They actually have to go through and read the entire database page by page, right? The more pages your database has, the longer these processes are going to take, and that might cause interruptions or issues depending on how you're set up and operating. So if you're using compression and you can fit more information in fewer pages, well, then maintenance shouldn't take as long either. Also memory, right? Memory is still today way more expensive than disk, and it's also faster than disk, right? Really, really fast disks are great, but the only thing faster than a really, really fast disk is not having to read from it in the beginning because the data is already in memory. So if you got the ability to store more data in memory, which some of these compression methods let you do, you can come out ahead that way. And if you're curious what you're looking at here, this is hand-woven ferrite core memory. This is a total of 18 bytes in the space of about 2 by 3 inches. So yeah, at least memory's come a long way, right? And finally, I/O, even with today's super awesome fast networks and everything else, I/O can still be a bottleneck, right? I've brought into so many clients over the years that have had, at the root of their problems, I/O bottlenecks. So if we have compression in place again, we don't have to worry about the amount of I/O we're doing, or we're doing less I/O to begin with, and that can help relieve some of these issues. All right, so first off, in our compression primer here, we're going to talk real briefly about lossy compression, right? And lossy compression has kind of weaseled its way into absolutely every aspect of our lives, right? On the right, we have the nice image there. Obviously, image compression has been around for quite a while, and it's been lossy. You have your JPEG formats or your newer HEIC encoding, which Apple tries to force upon the world and hasn't really worked that well yet. Music is a great source of lossy compression, right? MP3 is lossy compression. You lose some of the quality, but not enough to where it really makes a difference. And back in the old days, we had to install Winamp and occasionally listen to llamas get assaulted because at least at the point when I was in college, Windows didn't have native MP3 support yet, right? So you were probably using something like this. And then finally, for a more modern approach, of course, we have streaming video, right? Which the entire world is usually watching these days. And there's a whole bunch of advances in the world of video compression, right? We have H.264 compression, H.265, which is even better. The official standard for H.266, the next generation, which will bring, hopefully more 4K content to streaming, was actually just approved last July. I was reading it a couple months ago. So lots going on in the world of lossy compression where we shrink down the amount of data for minimum loss in quality usually, or a variable amount of loss in quality. How much loss in quality can you tolerate? That's the idea behind lossy compression. And that's great for these things, but when we're talking about data, that's not so great, right? I don't want compression to affect the data that I'm storing, right? For that, I need lossless compression, because if compressing something changes when I'm storing to the point where I can't get my original values back, that's bad, right? And I have a picture here of, floppy disks, which probably nobody has touched in a whole bunch of years anyway, which is great. But the idea here is lossless compression is what we'll be talking about today. We want the data to take up less space, but be able to reconstitute it to exactly what it was before, so it makes no difference. Now, if we want to take a little academic sidebar here, I'm going to mention Huffman Coding very briefly. This is an optimal an optimization for encoding more frequently used data with fewer numbers of bytes, right? And we'll talk about a little bit more about this later, but just to bring that up, that's one of the oldest forms of compression or optimization. It was like an MIT paper in the 1950s or so. Most of the compression methods we use today are more statistical in nature. So you got your LZ 77 and 78, which were kind of the originals, which actually came out in 1977 and 78. And those have served as the basis for a lot of the more modern algorithms, LZW, LZMA, gzip. These all basically work around the idea of creating a dictionary of most commonly used patterns and then referencing them with pointers where they're appropriate. And lossless compression like this has worked its way into pretty much anything you can think of, even if you're not thinking about it. Microsoft Office files have used zip compression since 2007, I believe. So if you've never taken an XLSX or a docx or a PPTX file and changed the file extension to .zip, you can do that and actually browse it, and you'll see a bunch of XML documents and a folder structure in there. That's exactly what that file format is at this point. All right, so we have some great compression technologies, both lossy and lossless. So when we're trying to compress our database, how are we going to do that, right? Why not just zip or do something lossless compression to the MDF file and the LDF and just compress the heck out of these files? You can actually get pretty good compression by doing that, but it's going to fail on a whole bunch of other fronts because of how the database works, how SQL Server is working, right? So database I/O is usually very, very random, and it's usually pretty small, right? We're reading from the disk in units of extents or pages. And we're not needing the entire file at once. We usually need a very, very small part of it. Because of those needs and the addition of performance, right? If we have great compression, but it kills the performance of our database, then why even bother? The SQL Server team kind of had to, when designing the compression features, had to take in the balancing act of we need pretty good compression, but we also need it to be really, really fast. So that's what they ended up coming up with. And this is great for, great for the large amounts of data that databases have, especially today. And as an added bonus, this data is also compressed in memory. We'll see that on another slide. But when you're using compression like this, the data is compressed both in disk and on memory. Actually, it was on the next slide. So here I have a very brief diagram, very simple diagram of a database system, right? We have a user, they're using SQL Server. SQL Server has a section of code called access methods, which basically translate the data from bytes on disk and in memory to tables and objects you can actually work with. And the access methods are actually where the compression occurs. So as I said, data is compressed both in disk and also in memory, which is great because we can not only fit more data on disk, we can fit more data in memory at any point in time. That's the upside. The downside of this is that because the data is compressed in memory, it is never cached in an uncompressed state. So if I'm selecting the same group of rows from a table 10,000 times, then guess what? SQL Server is decompressing that data 10,000 times as well. Right, so you're paying for this in terms of CPU load, very, very small CPU load. Back when this feature came out initially in SQL Server 2008, it was like 5% CPU load. Now it's got to be even lower, assuming you're using better hardware than you had in 2008, but it is CPU work nonetheless. So the three types of compression we're going to talk about today, here demonstrated by the most complex PowerPoint animations I've ever done. We have row compression, we have page compression, and then we'll also dive into Columnstore as well and talk about the algorithms that Columnstore is using to help achieve what it achieves. So first off here, let's talk about row compression. Row compression, some people might even say it's not really compression, it's an optimization, but what it is it's only use the space you need compression. So the first thing it does is it takes any fixed length numeric data and makes it variable length only using the necessary bytes. So if I have a column that's an int, right, and an int is 4 bytes and can store a value up to 2.7 billion or whatever, but I'm only storing the value 5 in that particular row, well, I don't need 4 bytes to store the value 5. I can actually do that with a tiny int, which only takes 1 byte. So if you're using row compression behind the scenes, what it's actually doing is storing that value in the amount of bytes it needs. And we'll actually take a look and see how that happens in the demos in just a tiny bit. So it's only based on the value it needs, or that's being stored, that's exactly what is being stored on disk, and it's saving all that space. Similarly, if you have fixed length character data, so if you have like a char 100 and you're storing someone's name and their name is Stu, and that's only 3 letters, that only needs 3 bytes, not the 100 that it would normally take if you weren't using row compression. Similarly, null and 0 values have been optimized away. They need no space at all. And if you have the metadata for variable length data, which is always there, the overhead for that is also reduced because there's a different record structure being used. So while normally if you had a variable length column, so let's say you had like a varchar 50, that of course would take up to 50 bytes depending on what you're storing in the column, but there's also 2 bytes that are added on to that as overhead, which actually store the length of what's being stored in that column. So if you had a varchar 50 and you had something that was 50 characters long being stored in it, it would take up 52 bytes on disk. This has been optimized away, so instead of taking up 2 bytes per column, it now takes only 4 bits per column. And this is done via what are called column descriptors, which again, we'll look at very shortly. Row compression does not have any effect on the smallest of the data types. So if you have something stored in a tiny int, well, it's going to stay a tiny int or small date or time. It does help bit columns though. It optimizes that a little bit as well. So if you have normally if you have a table and you have put a column in that table of type bit, right, which only takes up 1 bit because it's storing a true or a false, well, behind the scenes, SQL Server would actually allocate an entire byte for that, so 8 bits. And then if you had more than 1 bit column, or you added one later, those would share that same byte. However, this has been shrunk with row compression, so now you only need 4 bits instead of 8. So that's kind of cool. And then finally, if you have Unicode character data in your table that you're applying row compression to, that may be compressed. It will try using what's called the SCSU algorithm or standard compression scheme for Unicode. If that provides an advantage, it will go ahead and do that for you. Otherwise, if there's no advantage, it will not. So enough words. Let's try to just see this in action through something graphical here. So I have a table with 3 rows. I'm storing an ID, which is of type small int, which is 2 bytes, and I'm storing some first names of character 8, right? So those will take up 8 bytes. And normally without compression applied, this is how exactly it would look on disk. So Sam's name, even though it takes only 3 characters, well, guess what? It's taking up 8 on disk because it's a character type. It's a fixed width type. Now, if we apply row compression to this, it's going to shrink all this down as much as it can. So Sam's ID, which is 92, well, that can fit in a single byte. So instead of that small int taking up 2 bytes, now it takes up 1. Sam's name only takes up 3. And we save the rest. Similarly for Nick, well, his ID is larger, so it would take up 2 bytes, but his name doesn't need all 8 bytes, it only needs 4. So you end up with 60% savings on the first row, 40% on the second row, 10% on the third row. As I said, though, what this is doing now is the fixed width types are not fixed width anymore. So now we actually have to go ahead and read some metadata before we read each row, right, called a column descriptor. So we know exactly how much space that's going to take up and where these values are now with compression in place. So with that in mind, we're going to move to our first demo here. And I have a notebook, and all this data and the notebooks are available for download here, and I'll also have them up on the 8KB page as well, or 8KB GitHub repo rather. So the data I'm using today, this is parking tickets data from the city of Chicago. They released this a while back. So I have literally all the parking tickets that the city of Chicago wrote from the years 2003 to 2016. It's like 39 million rows. So just so you can see here kind of what data we're dealing with, we have some tickets, we have license plates, type of car, make of car, when it happened, where they got the violation, what it was for, what they paid, who wrote the ticket, what happened to it in court, etc. So we have all this data here, and we're going to start off just by taking a subset of this data, right? I have 39 million rows, and while I definitely could compress it all, it would take some time, and I don't want to sit here and make small talk while we're waiting for things to run. So I'm going to take a 100,000 row subset of that and put it into a different table called parking tickets mini, right? And that takes a fraction of a second, which is great. This is really fast to work with. So we have 100,000 parking tickets in our table, and if we want to see how big that table is in its current state, just without any compression at all, I'm going to run this query. It's going to join partitions and allocation units and a couple things together here. And we'll see that we have the table called DBO parking tickets mini. It's got 100,000 rows in it, and it's using a little over 12 megabytes for all this data. Great. So now I'm going to go ahead and apply the row compression, right? This is an alter table statement because I'm doing it on the table, not on an index. Rebuild with data compression equals row. And that should be nice and fast. There we go. Again, fraction of a second for 100,000 rows. So now let's run that same query again and see how that affected our size. So we took it down from a little over 12 megabytes to a little under 11. So we saved about a megabyte on 100,000 rows, doing some very, very trivial compression compared to other methods we have at our disposal, right? So this is the simplest, and we saved, almost 10% just by getting rid of white space and fixing more or less data types by changing them behind the scenes to more appropriate data typing. So now we're going to list out the pages that make up this table. And you used to do this with dbcc ind. However, now we have this sysdm database page allocations function that we can call. So I'm going to call that on this particular table, list out the pages, and I just want to find the first page of the table. I'm filtering them out here. We don't have them all, but I need a page number. So there's our page number, and now I'm going to open a separate window, and we're going to run dbcc page and actually look at the contents of this page. I love Azure Data Studio and I love notebooks, but based on a whole bunch of experimentation by yours truly, it looks like dbcc page does not play very nice with a notebook, probably due to the amount of text it spits back at you. So, and I can't blame them for that because dbcc page isn't supported to begin with. So we're just going to run it in a normal query window instead of a notebook. We have to enable trace flag 3604 if you've never run dbcc page, and then we specify our database name, the file number, the page number we want to look at, and how we want to view that page. So we're saying option number 3, which is show the full details of that page. We're going to run it, and it's going to spit back a whole bunch of information here of the contents of that page. We have buffer information, We have the page header, which has a whole bunch of information just about this page, what page number it is, what page is before it, which one is after, what object is this, etc. We get allocation information, so GAM, SGAM information, and then we get down to the records themselves. And I'll zoom in here. I realize this might be hard to look at on the video. The first thing we have here that we're going to see as I zoom in is we have what says CD array, right? This is that column descriptor array I told you about. And there's one of these for every row. And what it does is it describes the length of each of the columns in this row. So column number 1 is a 4-byte short. Column number 2 is a 7-byte short. It's showing the length of these because remember, we can't trust on the fixed width nature of the data typing anymore because we've applied compression to it. So we have this column descriptor array that gets added for each row. And then if we scroll down a little bit more here, we'll see we have the actual contents of the record itself, right? Just the flat out memory dump of the record. And you can actually read in text what's in here, what's in this record. And then below that is where we actually break out each column of the record and let you see what is stored for each. So we're going to look at our first column here, which is this. It's a ticket number. It's a ticket number 36566-295. This column 1 is a big int data type, right? So huge number of range it can store. It takes up 8 bytes of fixed width normally, but the value we're storing here right now doesn't need 8 bytes of fixed width. It only needs 4, which is why it says length 8, but length physical is 4, right? So we get a 4-byte savings on this value just by getting rid of the unused space. Similarly, we can go down and see other columns that work the same way. Some compress better than others, some maybe not at all. We have the state here. It's a Chicago ticket, so it was written in Illinois. You can see that the length of that column is 2, and the length is 2 because it's filling up the whole space. Some of these down here have some slight savings. The price has a length of 5 and a physical length of 2. We're saving a byte here, a byte there. Sometimes the savings is great, sometimes the savings is not so great, but you're trimming off that unused space. So if you run dbcc page on a compressed column, or on a compressed object, you can see this, right? So here's the next row, another column descriptor array, and more of the same. And you can just read through the whole page this way using dbcc page if you really want to geek out and see what's being written to disk. So that is row compression in a nutshell. John, do we have any questions at this point?
We do. We have a couple.
Okay.
The first one comes from, and if you ask a question, I butcher your name, I sincerely apologize. Lori, how will row compression affect text searches?
How will row compression affect text searches? And by text searches, I'm assuming you mean just standard where text column equals something, something. Right? If you're talking about full text searching, that's a completely different setup, and that's not covered here. But for any query or text comparison, this will work the same way. So there's nothing you need to do. In fact, this is pretty transparent to end users or applications that you can compress things behind the scenes, and it would not be apparent to the queries they're writing.
Okay. Another one from London DBA. Any benefits on the transaction log from using compression? Thinking less space used for the logging data modifications, and he says row compression data.
So I am not exactly sure. I don't believe the contents of the log are compressed. I guess if the compressed output might be what's actually physically written to the log. I'm not exactly sure on that, so you may see some savings.
We have another question from Michael Thomas. What is the downside of row compression?
What is the downside of row compression? I would argue there isn't much of one other than it's a little more work, right? I used to, back in the day, I used to advocate for, as long as you weren't bumming your CPU up against 100% constantly, you should probably enable row compression because it will likely help you. If you can prove it provides no benefit, I wouldn't use it. We'll talk about how compression used to be an Enterprise Edition only feature, so that would have been a potential downside, but otherwise, I would argue there isn't really much of one.
Okay. Next one is from Lars. Actually, we're getting a ton of questions now, so
Oh
at some
boy,
point
all right.
I'll cap them and
I
we'll
would
just
say,
move
yeah,
on.
we get a couple more and then we got to move on so we don't run out of time.
So the next one from Lars: does index compression mitigate poor fill factor settings?
Does index compression mitigate poor fill factor settings? I mean, you can fit more onto a page, and that can't, but it's still going to count the page as full when it reaches your fill factor setting, right? So I would argue no, other than you get the benefit of storing more data per page to begin with.
Okay, so how about two more?
Sure.
The next one's from Roman. Is there a way to compress data in TempDB?
Is there a way to compress data in TempDB? Not that I am aware. These compression settings we're talking about here do not work on system databases.
And one more from
oh, wait a minute, no. Well, system objects in system databases does not work for. If you want to create a temp table with compression, I believe that will work. But I haven't tried it. Sorry.
No, you're fine.
Yeah.
One final one, then we'll move on. Ajun asks, does row compression lead to more page splits? If yes, how can we avoid?
Would it lead to more page splits? If you have a pattern where you're constantly overwriting data and your data is taking up different amounts of space. So if I have, like my first record that's on the screen here for Sam, and then I overwrite Sam and put a longer name, all right? If I was using fixed width, that wouldn't be a problem, and it definitely wouldn't cause a page split. Whereas if I'm overwriting something and the record no longer fits there, that might cause a page split. So I guess it might cause more page splitting. Not sure if that would really be a huge issue or not. Maybe if it was in your particular environment.
Okay, so I'll go ahead and document the rest of the questions.
Awesome.
For the audience, make sure you put it in the Q&A, and I will capture them, and I'll make sure to get Bob the list of questions.
Very good. Thank you so
Thanks,
much,
Bob.
John. All right, thanks for the great questions. I'm glad people are enjoying this. All right, so we're going to move on now because row compression is cool, but page compression is even cooler, right? So page compression takes row compression and kind of kicks it up a notch. It actually has three components of what it's doing. So first thing page compression does is row compression out the boot. So if you put page compression on something, you're automatically having row compression take place. And then beyond that, you have what's called column prefix compression and column dictionary compression. And we'll talk about what those mean here in just a moment. In addition to the column descriptors, you now have what's called a CI, or a compression information structure, that is added to each page, which contains what's called an anchor row and the dictionary of the data that's in that page. Page compression may not be applied to every page, so SQL Server is actually doing some work behind the scenes to determine if space can actually be saved by page compression. And if the data that's on your page is not going to see any benefit from it, it will not apply page compression to that page. And then finally, page compression only applies to the leaf level pages. So in the picture on the screen here, where we have our index structure, the leaf level is the bottom row, 4, 5, 6, and 7 in the lighter green. The upper levels of the index, which generally just contain pointers to other pages that have the actual data on them, those do not get page compressed. So first thing we'll talk about is prefix compression. It will try to find a prefix for each value in terms of byte values. So it'll be type agnostic, right? Whether you have a numeric value or an integer or text or a character or whatever, it will just be working with the bytes here. So it doesn't care about the types. And it will try to find the largest, most common prefix for all the records in that column on that page, and will determine that prefix to be what's called the anchor record. It will store it there. And then row values are translated to be in terms of that anchor value. So if I had two values here in bytes, as I do on the screen, and I'm looking for my most common prefix, well, 0, 1, 2, 3, 6 is my common prefix there. They both start with that. After they differ, even if they're the same after only one byte, doesn't matter. We're looking for the most common continuous starting prefix. So we have a database page here. And this page contains information about 3 rows, each with 3 rows with 3 columns. And we have our page, we have a page header, and we have that CI, that compression information structure. And we're going to go ahead and perform page compression on the values in this page. So the first thing we're going to do is create that anchor row that I talked about and try to determine what is the most common prefix for that column, and then we'll put it in the anchor row. So for the first column, The most common value with the most common prefix is AABBC, so that's going to be our anchor value. Similarly, for the second one, the longest one with the most common prefix is the first one, AACCBF, that's our anchor. And for the third one, it's BCDFA. Once we have our anchor row, we then go ahead and we transform the data to be in terms of that anchor row. And I'll show you what that means. So for our first row and our first column here, the value is AABB and our anchor is AABBC. So what we need is we need the first 4 values for first 4 bytes of that anchor column to be stored. So that's what we're going to store. Instead of storing AABBC, we're going to store 4. And that means just go to the anchor row and get the first 4. Okay, hopefully that makes sense. For the second one, now we have CAB. Well, that doesn't match, right? Because this starts with C and our first value in the anchor column is A. So that doesn't match at all. So what we store then is we store 0 CAB, which means go to the first 0 values of the anchor column and then put CAB after that. Now I'll point out this does not save space. This actually costs a little more space, right? Before we were just storing CAB, now we're actually storing a 0 in front of it. So we had to expand it because it didn't match the anchor column. The third one is AABBC, which is the anchor value. So we're going to store null. And it's not really null, but a special type of null that means point back and just display the anchor instead. So that's what we're storing here for this first column. We translated it to be in terms of that anchor record. Similarly, for the second column here, we have the first value is the anchor, so that gets a null. The second one is AACC, that is the first 4. The third one, AACCDE, well, that's a CDE. That's the first 3 of the anchor row followed by DE. And then the third one, third column, null again, BCB, which means 2, get the first 2, and then put a B after that. And the third one is CAB, which is not the anchor column at all. So we have to say 0 CAB. So this at the end here, this is what prefix compression looks like. And hopefully this makes sense. But again, we're taking this anchor row, this anchor value for each column, and taking the rest of the data on the page and putting it in terms of that anchor value. And we saved a decent amount of space here. But that's not all that page compression is doing, right? So then we're going to actually go ahead and do dictionary compression, which is then going to deduplicate on top of this. So it's going to look for common byte values across all the columns on the page and create a dictionary and store these entries as a 0-based array. And then that's stored in the compression information structure after the anchor row. And entries in the dictionary are only created if a value is repeated in 2 or more columns. So we're going to go back here to our page, how we left it last time, and now we're going to apply this dictionary compression to it. So we're going to create our dictionary here in the compression information structure. And the first thing we're going to do is find, well, the value 4 is in more than one column, and it's twice. So we could actually put 4 in the dictionary. And instead of storing 4 multiple times, now we're just going to put a pointer, in this case, array 0, into that dictionary saying, hey, go to the dictionary, get the value from the dictionary, and then apply that dictionary value to the anchor value to translate back into the value that was being stored beyond that. So we saved even more space by deduplicating now. Second thing, we can do the same thing with 0 CAB because that's stored multiple times in more than one column. So now we can say, hey, that's dictionary entry number 1. So there we have it. We took this page and we actually compressed it down using both header or prefix and dictionary compression. And now that I did that, we're going to go back here and we'll move to the rest of our demo on that. Okay, so I'm going to use the same data I did last time, but now I'm going to take our mini table with 100,000 rows and I'm going to rebuild it with page compression instead of row compression. And that'll be pretty quick again. And now let's see what page compression did to the size. Remember, we were originally at a little over 12 megabytes, and then we got down to a little under 11, and now we're at 5.25, right? So we shrunk this over 50% from the original uncompressed size using page compression, right? By deduplicating and building these dictionaries and whatnot. So that's awesome. Now, if we want to see, again, like what's this actually physically looking like via DBCC page, we're going to go and get the first page of the table again because it changed when we rebuilt it. We're going to grab that page value here and move back to our other window, plug that page value in and run DBCC page and see what our data looks like now. So we're looking at our page again. We still have a page header and allocation information, But now we have the interesting stuff. We have, and I'll zoom in here, you can see we have compression info, right? This is the compression information part of the page, right? And it's going to spit out the raw bytes for us. And if we scroll down, we'll start to see a bunch of the data from our data set that's pretty repetitive. For example, we have all the makes and models of cars in here, right? Buick, Dodge, Ford, Honda, Hyundai, lots of those in that data set. So those are being put in the dictionary along with a whole bunch of other information that's repetitive. We also have information I'll show you real quick in here. We have page modification count that's kept track of, and we'll explain why on the next slide when we're done with this demo. We have some header flags showing, yes, this CI has both a dictionary and an anchor record. And then we move down into our column descriptor array, because again, this does contain the row compression before the page compression. So we have the row compression information again, and then we have the actual memory dump. If we scroll down a little further here, we have entries pointing to that. And let's get down to where we can actually see, this is the dictionary it's going through here. We can actually see a record. So here's a record, a real record. We'll take a look at this. We have our column descriptor array, but let's get down and see the actual columns themselves. So, right, column 1, whereas it was a physical length of 8 and a length of 4 before, it's actually 3 now. It was able to shrink it a little more with the page compression. Some of these actually went down to 0, right? We have the state, which is Illinois, again, Chicago tickets. So we'd see a lot of records from Illinois. So Illinois is actually in the dictionary at this point, which means the physical length being stored is nothing, right? So length 2, physical length 0, same for passenger vehicle below it. So now we're getting much more compression out of this dictionary and deduplication that's taking place. And because of that, we were able to save over 50%, right? So that is that. I will point out very quickly, if you'd like to find out how things are compressed with row or page compression, that is, it's at the partition level. You can actually compress things differently per partition. So I have some queries here where you can run and see all your partitions and see how they're compressed, right? So the main table is not compressed at all. The second one is in page compression. I have some other demo queries here. For the interest of time, I'm going to gloss over these, but you can see what features are being used by the database that are enterprise or used to be enterprise. Compression is no longer an enterprise feature as of SQL Server 2016 Service Pack 1, but it still shows up in DB persisted SKU features. So you'll see it here listed. And then there is a compression savings stored procedure you can run that will actually go and simulate for a data set how much space can be saved. Okay, so with that, I'm going to drop this table really quick and we'll move back to our slides here. As I said here, we'll talk about just a little bit more. Compression information structure that we went that contains that dictionary and that header row, that is rebuilt on an all or nothing basis. And it's not rebuilt every time you update a page. So if you just update a single row, it's probably not going to trigger a rebuild. I showed you how page modifications are actually tracked in that compression information structure. And the way it works is if the page is modified more than 25 times, or if the more than 25% of the number of rows on the page are modified, then it's going to try to rebuild the compression information structure, but it's only going to actually do it if the rebuild creates enough space for 5 or 25% more of the rows. All right, briefly, I'll gloss over the syntax, but this is done at create or rebuild time. You set the data compression value to none, row or page. You can do this on tables. You can do this on indexes. You can also do it on individual partitions. So you can change your compression up and say, I'm going to partition this index where, partition number 1 is row compressed and partitions, all the others are page compressed. You can actually do that with the compression syntax. You can rebuild individuals and decompress. If you compress the clustered index of a table, your non-clustered indexes do not inherit out of your compression settings. They are completely separate. And if a clustered index is created or dropped, the result will inherit the compression setting that the heap or the index had. So it's not going to just change the compression because you created or dropped a clustered index, is what that's going to do. Common questions I get, big one is data compression and TDE. How does that work? Do they play nicely? Actually, they do. If we go back to this diagram I had here where I talked about how the access methods was where compression takes place. So everything in memory and on disk is compressed. Well, TDE encrypts everything on disk, right? So at this point, we are encrypting data that has already been compressed. That will work absolutely fine. If they were switched around, if we were compressing data that was already encrypted, that would probably not work very well for us, because remember, compression is trying to find patterns and eliminate duplication, whereas encryption is taking something that has patterns and duplication and making it look more or less completely random, whereas most compression algorithms probably would not get you very far at that point. This is not backup compression. This is shrinking the data in the database in hopes of fitting more data on a page, whereas backup compression is another proprietary algorithm that's compressing the backup stream for sole benefit of making the backup files smaller. You can use backup compression on a database that's using row or page compression. Your backup compression will not compress quite as much. You won't get the same compression percentage than if you were compressing data that was not row or page compressed, but they will play nice together and they will work. There's nothing that says you won't. If you're trying to deduplicate your backups or something, generally you'll get farther with deduplication if you don't have row or page compression enabled, but this is something you would need to test in your environment with your hardware. So what can't be compressed? I know we had with these methods, I know we had a question about that earlier. You can't compress system tables, and you can't compress anything that's not on a data or an index page. So if you have like binary or lob data or file streams or nvarchar max, those will not compress with this method. How much space do you save? Well, it really depends. It depends on the data you're trying to compress. So if you have proper data typing to begin with, you're probably not going to save a whole lot in the way of row compression. And if you have not a whole lot of repeating data, you might not get very far with page compression. But again, you can use SP estimate data compression savings to try to estimate that. That's going to go ahead and reads like 5% of the data into TempDB, basically goes and reads every 20th page, and then we'll try to compress that data and extrapolate the results for you. And finally, about compatibility here, row and page compression that we talked about were introduced in SQL Server 2008, and it was Enterprise Edition only at that point, but then in SQL Server 2016 Service Pack 1, they removed it from Enterprise Edition, so you can use it in Standard Edition now. Also, if you are using sparse columns, you can't use row or page compression. In all my years, I've never come across an environment that was actually using sparse columns, but because sparse columns is a different type of row storage technology, it does not play well with the compression features. And if you want to know when to use it, it's most effective on tables with a really high number of scans, or data that's seldom accessed is great too. Should you use compression all the time? You can if you have the CPU to burn. It's got some intelligence in it to where it's not going to compress things where it knows it can't actually save space, so it has that working for it. I'm not a huge fan of the environments when I come into sometimes, and there is an edict from on high: all tables will be created with page compression. Why? Because we said so. Based on what? So that's kind of where I don't think you should blanket use it, but if you do, it's not a terrible thing, especially with the power of the CPUs that we have now. Remember, this was like a 5% CPU hit back in 2008 when this feature came out. Hopefully you're using way better hardware than that these days. What if my storage array does compression? Sorry, I'm trying to preemptively ask questions here. If your storage array does compression, if you got a new hot storage array, test it out, try it. Your storage array probably has big honking CPUs that can dedicate a lot more time to a lot better compression than SQL Server, which is trying to compress and decompress this data and service all your queries and everything else that's going on. So you'll probably get better compression from a storage array, and you're not using the database CPUs to do this work. One of the bigger downsides is your data will not be compressed in memory anymore. But again, if your space saving on disk is worth it, that might be worth it for your environment. But this is something you really need to test. John, I'm sure we have more questions.
We have a whole slew of questions.
Oh dear.
I've been typing nonstop. So.
Oh God. Okay.
And I'm going to try to pick out some questions that are related specifically to like page compression, since that was the subject you're on.
Okay.
So Tim Brown asks, is the prefix a set size / list of sizes, or is it arbitrary?
It is, as far as I know, it's arbitrary. That compression information structure is not a set size. So I think it's, if you have a varchar 1000, I don't think that's going to end up being your prefix, but I do not know of a maximum if there is one.
Okay. So Frank asks, is the anchor row always the longest value in the column?
It is the longest value with the most common prefix in the column. So it might not necessarily be the longest value. It might have been that in my my demo, they also happen to be the longest, but it's the longest value with the most common prefix.
And I saw, oh, there's Frank's. Okay. London DBA asks, for a high OLTP table, would you recommend using row compression over page compression?
I would recommend testing and seeing. I think page compression could also work well for a high OLTP table. Row compression will be a lower hit, right? Nothing's free, so every time we do a little something, we're using more resources to do it. Row compression would definitely be less of a hit, but I bet you the hit for page compression would also be trivial, at which point you might want to try that if it saves you more space.
Okay. Blake asks, would you recommend page compression on a table that has a high number of inserts, updates, deletes, or would that just cause it to rebuild too often?
I would recommend testing. This is one of those things where you need to see how it performs in your environment on your hardware with your data, is what I would say. I do not shy away from saying you should at least try page compression, but try it in dev, try it with a real workload on some real data if you can, and see if it makes a difference or not.
So I've got, how about three more? Can we do
Sure.
three more?
Yep.
And you got about 15 minutes, I think, time-wise.
Yep.
Tim Brown asks, can you compress table variables?
Can you compress table variables? I do not believe so. I'm not 100% sure, but not that I'm aware of. Let's put it that way.
Okay. Two more. Andrew Jackson asks, how does each compression type influence index seeks? I'm guessing that the compression only applies to the table data and not the indexes.
So the compression, well, it applies to, if you compress the index, it'll apply to the index as well. It doesn't apply to the upper rows of the index, but it will apply to the index itself. So what was the question again? Does it apply? Was that it?
How does each compression type influence index seeks?
It doesn't influence them, other than it's a bit more work to decompress the value as it's looking it up, would be my thought.
Okay, and we have a question from, and I apologize, I'm a horrible American. I'm gonna mispronounce the name. Marcy, what happens when we have row compression and we update a value from int? He says int to int, but I'm guessing he's going from a tiny int to an int.
From a tiny int to an int, so it won't stop you. I believe what's actually happening behind the scenes, because it's compressed, I believe it's a metadata operation at that point, is my first thought, at least. There's members of the product team here who are telling me I'm wrong. I'd love to hear your answer, but I don't believe it would cause an issue to do that. That'd be my thought.
I've never tried.
Yeah, I haven't either. Hopefully.
Okay, so,
Argenis says, yeah, he's all right. So maybe that means I'm right. Maybe he's talking about someone else. Probably someone else.
I think he's commenting about my horrible American, because
there we go.
Horrible
all right.
names.
So cool. All right. Thank you. I'm glad we're getting good questions. I'm glad people are enjoying this. All right. We're going to keep moving on here. We're going to talk now about Columnstore, right? Which is an awesome technology that I could probably spend a few hours on, but we're going to try to boil down Columnstore a little bit. And Columnstore has changed over the last, 9 years now. It was first introduced in SQL Server 2012. So just briefly, if you are aware or not aware, Columnstore was introduced in SQL Server 2012. At that point, it was for non-clustered indexes only. It was read only, and it only worked in Enterprise Edition. So if you built a Columnstore index and you wanted to update the value, you had to drop and rebuild that index, right? It was kind of horrible. It was there, but it wasn't incredibly useful at that point. There were a lot of people, including yours truly, going, okay, how do I make use of this in a useful way? But they kept getting better, right? In SQL Server 2014, they added updatable clustered Columnstore indexes. So now you can have your data stored in a clustered Columnstore index. It was still Enterprise Edition only. And you could not have any secondary indexes on data that was stored in a clustered Columnstore index. 2016, things got way better because they added non-clustered Columnstore indexes that were updatable now, so the data could be updated. You could also create secondary B-tree indexes on that, and big thing, they made it available in Standard Edition, which was awesome. You needed 2016 Service Pack 1, same thing as the row and the page compression. And in 2017, they added adaptive query processing for tables that had Columnstore indexes on it, so that it could automatically choose like the physical table join type based on rows and other information it has, and you could add computed columns to clustered Columnstore indexes. And then in 2019, they gave us online building and rebuilding of clustered Columnstore indexes. Now, if you're not familiar with how column store indexes like physically work. Graphically, we'll just very briefly go in here. If this is a regular relational table with your rows and your columns, a column store index would look something a little more like this. We have the data that is broken up into groups called row groups. And then within a row group, data is compressed on a per column basis. Okay, a row group is usually 1,000,000 rows. It's actually 1,048,576 rows, 1 row per byte. That's in a megabyte, actually, is how that works out to 2 to the 10th power. So we have our row groups, we have columns. Each one of these boxes here in the column store is called a segment. So a row group consists of 1 segment per column for all that. We also have what's called the delta store. And there are delta row groups. There can be multiple delta row groups per column store index. Maybe not necessarily 1 per row group, but you can have more than 1. And then collectively, this is usually referred to as the delta store. And what this is each delta row group is essentially a B tree index, just like a non-column store index or a row store index, we can also call it. And this has information about what has changed. So if you insert rows into a column store index, they don't get added to the actual column store immediately. They get added to a relational table or relational structure in the delta store. Similarly, if you delete rows from a column store index, the delta store gets modified there. And when the column store is read, the delta stores are checked and then changed. The output is changed based on the contents of them. And then as delta stores get larger, the column store row groups may need to get rebuilt behind the scenes. This is done by a process called a tuple mover that handles that for you in the background. So column store compression algorithms, there's actually a whole bunch of them. I just talked to you about how row and page compression works. Column store has a barrage of algorithms it can use, and you don't get to pick. When you say put a column store index on this data, the engine is going to go through, profile that data, try to figure out what's best, and then build based on that. So we're going to talk about what some of these are. Column store indexes are still kind of a black box, so I don't know all of the ones that are involved, but here's some of the ones that I do know exist. One of the simpler ones is called value-based encoding or value scale, and this is trying to create a mathematical relationship between values and what we're storing. This works only for numeric and integer types. So let's say we have a column here with some integer values in it, and we profile this column and we see our minimum value is 1105, our max is 1122, and because of those values, we need 11 bits to store these values for each row. Okay, if we're doing value-based encoding of that, well, we can just simply subtract the minimum, right? And now our minimum is 0 and our max is 17, and that only requires 5 bits per row to store. It will create what's called the base value, which in this case is 1105, which is the minimum, and subtract that, and now it takes a whole lot less space to store this information and to read it back. While we take the values we're storing, we add our base back to it, and there we go. And this doesn't just have to be subtraction. This can be other mathematical operations that are more complex, but subtraction is great to show for demonstration purposes. So that's value-based encoding or value scale encoding you can do. There's called a bit array version where it will take and make a bit column for each distinct value found. So if we're working with a column here that contains blood group information, that's pretty distinct. There's only 4 different major blood groups, right? So what it would actually do is create a column for each of those and then set the bits for whichever one the value is in. This can speed up things like predicate search, right? We don't have to scan the information to see what values are in there. We can just read the column headers. We know it that way. If we're doing joins, we actually join against a bit mask that we have here and get our results that way. So this is, if you have a very small number of distinct values, this might be something that's chosen. We also have dictionary encoding, right? Dictionaries are great for compression. We've been talking about them this whole time. So let's say we have our parking ticket information again and vehicle make, right? So we have some Chevys, some Ford, Audis, Teslas, etc. If we encode these, we can create a dictionary, and now we're storing a numeric ID, which takes a lot less space than all those strings, right? And if you think about it, what this dictionary kind of is like creating a lookup table in a relational database, right? So we have our lookup table, which is the dictionary, and now we're just storing the value or the ID for that. So the number of bits for ID is much lower, and this also kind of makes it data type agnostic at that point because our dictionary can have whatever in it, and we're just working with numeric values. Touch on Huffman coding again briefly, just to talk about how, as I said before, it's an optimal prefix algorithm, and what basically it will try to do is determine which values are most common and represent those with fewer bits. So if I have information about cars again, Chevy is one of the major brands, at least here in America. So you're most likely to find like a Chevy or a Ford as opposed to a Bugatti, right? They make very expensive cars. They don't make a whole lot of them to begin with. So we would give that a higher ID that requires more bytes to store. And that actually saves us space in the long run because the most common values take the least amount of bytes to store, right? It would take 1 bit to store a 0 or a 1, 2 bits for a couple values beyond that, etc. So we can use the frequency and the probability of the occurrence to actually determine what gets stored there. There's also another one here, it's called run length encoding. This is where we can avoid repetition by grouping values together. This depends on the repetition pattern of the data, and your efficiency will come from that. So if we have a color column and we're storing red and blue, and we have 105 reds in a row and 92 blues in a row, we can actually just store the count, right? And we know that the first 105 rows have a value of red, and the second 92, the blue ones have 92. So we can save a ton of space, right? We're not even storing every row individually anymore. We're just having a summary of this basically is what we're storing. Get great compression out of it. But it depends on the ordering of your data. If your data is ordered differently and now we're alternating between red and blue, well, now it becomes less efficient. We need to alternate our run length data set at that point. So depending on your ordering, it may or may not use it. Can also combine run length encoding with dictionary encoding. So we'd have a dictionary we'd create, whereas now we have numbers, and now our run length values being stored are all numeric instead of containing text, and we can save some space that way as well. And now with that, I'm going to move to very briefly my Columnstore demo here. We're going to go back, and I should have had this building in the background. Dang it. Okay, I'm going to kick off this build of this Columnstore index. I'm going to build a Columnstore index on the entire data set, which is going to take about 1 minute and 10 seconds. So while that's running, I'm going to work through a couple more slides here real quick. Columnstore compression syntax is basically it's create clustered Columnstore index or create Columnstore index with data compression equals, and you get a choice. You get Columnstore or Columnstore archive. Columnstore is the default. If you don't specify anything, that's what you'll get. Columnstore archive basically takes the Columnstore structure and compresses it again on top of it using something probably like LZ77 in some modified form. But what it's doing is it will get you even more space savings at the cost of even more CPU effort to retrieve it. But if this is data you need in a Columnstore and you're not going to look at very often, that is exactly what they put it there for. All right. When should Columnstore be used? Well, if we have queries that scan really large amounts of data, especially on really large tables, if we have data sets with really repetitive values, we have any kind of data warehousing workloads, if we're doing real-time analysis on OLTP workloads, these are great use cases for Columnstore data. My thing is still building, but it should be done any moment now. When should Columnstore be avoided? Small tables, and I use small in quotes, tables under 1 million rows, they won't really benefit because it won't build a segment until it has about 1 million rows to work with. So at that point, you'd have a Columnstore, but everything would really be in your delta store and a B-tree structure, and it'd be no different. If you have columns containing lots of very unique information, Columnstore might not be able to help you with its compression. If you have lots of queries that just scan an entire table and return all the rows or are frequently updated, Columnstore isn't going to be a panacea for you and solve everything there either. I've seen so many environments I've come into where I'm doing performance tuning and they'll be like, well, I put a Columnstore index on it and that still didn't help it. Well, Columnstore indexes won't fix everything. Okay, back to our demo really quickly here. We built a Columnstore index on about 5 columns in this table: ticket number, license plate, license type. We can query some of the metadata. So I'm going to query sys Columnstore row groups, and it's actually going to show us the row groups that were created. We have about 37 million rows in this table, and you'll notice that it actually created 36 row groups. So there we go. Most row groups, I'll zoom in just to show you, have that maximum number, 1048,576 rows, and the couple at the end have a few less. But that's how it does the row groups. If you want to see what happens if we add a row to a table, here I'm just going to insert another row into my table, and then we'll come back and we'll run that query again just to look. Now we have another row group that was added at the end, but you'll notice here, and I'll zoom in, this one says open, and it has a hopped ID for a table structure for that delta store that contains that open row, because that row we inserted is not actually in the Columnstore index yet. If you want to look at the segments that are in the Columnstore index, you can run this query and see the various segments. There are lots of them because there's 37 row groups and times 5 columns. So a whole bunch of segments that get returned there. If we want to do some additional querying here, I know I'm just about out of time. I'm going to grab a hopped ID and I'm going to show you the dictionaries, and then we'll go for the big kahuna here. We're going to open in a separate window. I'm going to run a different undocumented command. You may have heard of this, you may not. It's called dbcc cs index, right? This is like dbcc page, but it will display for you graphically the contents of a Columnstore index. So we can look at that again really, really quickly here. Yoink. And see for column number 3, which is license type information. Uh-oh, incorrect number of parameters. What did I screw up? I've done this before, I promise. Hang on. I wasn't even typing, I was copying and pasting. Try this once more, and if it doesn't work, we'll nuke it, but I promise you this is a command that works. dbcc cs index parking tickets, grab the hopped ID that I need, and plug it in there. And it is failing. I don't know what exactly happened here. Why it's not doing that. Okay, we're going to abort this demo, my bad. Anyway, if you use dbcc cx index, you can actually unlock the contents of a Columnstore index and see what is in there, how things are being stored. It'll actually show you in the Columnstore segments column what type of compression is being used. I broke something good here, didn't I? Oh, because I have that hopped ID that I can't use. If you plug that in. Anyway, we're just about out of time and I want to leave time for questions. So first I will point you, if you have any questions, I would like to see further resources on this information. Here's some, there's even more at my website or on the 8KB page. I'll have the list there as well. If you go to bobpusateri.com/r/compression, you can see all that. John, do we have any questions we can follow up with quickly here?
Do we have questions? You're going to get a small booklet of questions I have listed.
Awesome.
So first up is, and again for the attendees, if I don't get to your question, I have them all documented. I will make sure Bob gets to them. Hugo asks, are we able to see which Columnstore algorithm was used in a certain table, like dbcc page?
You are able to see it from that that demo code I had up there. It will actually show you, where is it here? Encoding type. So it will actually display, you don't even need dbcc page to see this. If you go to sys.columnstore segments, that will show you the type of the encoding that's being used on the segment, right? So not at the table level, not at the column level, but the particular row group for that column, which is the segment. You can actually see what type of encoding is being used there.
Excellent. Max asks, is clustered Columnstore applicable on per partition basis, just like other compression?
Is clustered Columnstore applicable on a per partition basis? My first thought is no, because it's clustered and it has to contain all the data, but I haven't tried that. Someone can correct me if they're wrong.
Okay. Arthur asks, how can we monitor actual compression overhead? Are there any perfmon counters or weight types associated with that?
I do not know. I will have to look that up. I'm pretty sure there's perfmon counters for Columnstore indexes. I do not know if there are specific weight types for that, though there probably are.
London DBA asks, any DMVs that show us the contents of info for the Delta store tables?
Not that I am aware of, though you could definitely look it up with the hopped ID via dbcc page and see what's in there if you wanted. But yeah, not sure.
Okay, thank you very much. Matt asks, how does table partitioning affect, oh wait, we might have already asked that question. Anyway, how does table partitioning affect Columnstore indexes? I think that was asked and answered already.
Okay.
Looks like, already asked that question. Sunho asks, if two partitions on a table are compressed differently, row, page, Columnstore, what happens to the compression when you merge the two partitions? I
That's a
have no
really
idea.
good question. I have never tried that. I
I've
assume
not
you're
heard
either
it.
going to get an error or it's going to pick one. But yeah, I should have made this a little bit longer session. I apologize.
And I do have a follow-up that earlier in the earlier question segment from Marcy about we thought it was going from a tiny int to an int.
Okay.
Really, they clarified the question about if that column has a small value like the 5, and then you went from, and you have row compression, but you updated that column value from a 5 to that, 2 million and change, 2 billion and change. What happens?
What happens at that point is the row will grow in length, right? Because we need more bytes to store that value. So that'll be a matter of, can the row fit on this page still? Does it have to move somewhere else? Do we have to split pages or whatever? And the column descriptor information will change to show that this is that this is now a wider column and it needs more bits to store.
If they don't have any room on the page, then it would split the page and move it, right?
That would be my first guess. Would be that's how that's going to happen at that point.
And so there was another, I think, related question. What happens if we change from tiny int to like a big int?
If you change the type of the data, the data type of the column. So at that point, I'm not sure if it actually needs to rebuild the table or not, because in theory, it could be a metadata operation because everything's being stored in a state where it's using the least amount of bits that it needs anyway. So it might just be a metadata update, but I'm not exactly sure. I should probably write a blog post about this and find out.
And there was a question from Antonio, but I don't know if Argenis had answered that or not. How much regarding percentage of DTU in Azure could penalty page compression in an Azure SQL database?
I don't have any idea on exact numbers, but my first thought it will be a minimum impact, just like it's going to be a minimal CPU impact in general if you're not even running in Azure.
Couple more. I don't know what's our time limit.
I think our next person is starting in 9 minutes, I believe.
All right. So how about two more? I think that'll wrap everything else. So I think everything else got answered somewhere. Iowa asks about Columnstore. We had an issue with Columnstore and always on sync availability groups. At some point, the sync process would get overwhelmed and the queue of updates would shoot up. The process on the sync database would block any select statements from relevant tables, defeating the purpose of the secondary replica.
Wow.
And so there's an issue with ETL that was deleting latest day's data and reinserting it. Have you ever experienced anything like that? And if so, what advice would you have?
I have not experienced that. That almost sounds like something I would maybe consider contacting support about, just asking, is it supposed to happen like this or not? Because that seems kind of like it shouldn't block at that point, but not totally sure. And it never hurts to ask support.
Okay, so one more from Goran. When I look, it seems the numbers sized used in the database file and the actual size of the backup file follow each other. Is that just accidentally so, meaning the compression is just removing white space?
The size of the data file and the size of the backup file follow each other. Is this for a compressed backup or just for the data compression? Because
they don't clarify. They just
forget compression, right? The backup file is going to contain the data that's in the data file plus the active portion of the transaction log. So I would generally expect the file sizes to follow each other. Similarly, if you have data compression, if you apply data compression by itself, your data file is not going to shrink at all. It just might have more empty space in it. And then your backup of that would be only the portion of the data files that you're using. So I would expect your backup size to perhaps be smaller at that point when compression is involved, just because there might be extra space in your data files.
So they did clarify that it's for a compressed backup.
Okay, so if there's a compressed backup, then it's not. It might even be linear, but either way, it's going to be writing. It should be smaller than at that point than your data file sizes.
Okay. I think we have almost everything asked and answered.
All right.
So I know we're about out of time, but I do have all the questions captured for you, and I will make sure to send you that list that I have.
Awesome.
And I assume that people can email you or contact you with further questions and follow-ups.
They can reach me and contact me. I will write a blog post answering the questions that John sends to me. And thank you all so much for watching. I hope you enjoyed it. Sounds like we had a lot of questions at least. And yeah, let's get out of the way here so Gail can get ready for her
I will
session.
tell you that my mind is kind of between handling all your questions, and that was just capturing the questions, but mind melting content. It was great. Great job.
Thank you so much.
Absolutely fantastic session there, Bob. Huge discussions going on in the Slack channel as well.
Yep.
So you've got
dear.
loads of questions, loads of discussion going on. We need a prize, Anthony, for the first person to mention DBCC page in 8KB.
Right.
So fantastic,
Cool.
Brandon. And a new command as well that I didn't know about mentioned as well. So fantastic.
Agreed. I didn't know about that one either. The
Kind of
CS.
sad it didn't work. It works, I promise, but I'll figure out why it didn't work in my demo there. But yeah,
I'm
All
pretty
right,
sure
very
that's
good.
the best compression presentation that I've ever seen in my life.
Yes.
Yeah.
Well done.
Thank
I'm
you.
gonna grab the
Thank you.
screen.
All right. Yeah, please feel free. Thank you so much, everyone. I really enjoyed it.